Welcome to this explainer, everyone. Today, we're exploring what I think is honestly one of the most fascinating transformations in all of manufacturing. We're going to look at exactly how we take raw, brittle dirt right from the earth and engineer it into the high-tech, virtually indestructible components that you'll find in everything from rocket engines to artificial human bones. So let's get right into the forming and shaping of ceramics.
Take a look at the sheer variety we've got here. You know, when most of us hear the word ceramic, we instantly just think of pottery or coffee mugs, right? But chemically speaking, a ceramic is actually any inorganic compound made of a metal or semi-metal combined with one or more nonmetals. Because the atoms in these materials are locked together by incredibly strong covalent or ionic bonds, they're exceptionally hard, super chemically stable, and they boast incredibly high melting temperatures. But there is a major trade-off. They have absolutely zero ductility. They don't bend, they just break. So how on earth do we shape a material that stubbornly refuses to be bent?
Okay, let's dive into this by first understanding the two main categories we're dealing with. We've got traditional ceramics. These are your typical silicate-based materials, things like kaolinite clay, used for your everyday pottery, tiles, bricks, and cement. But then we have new ceramics. These are the advanced, non-silicate materials like oxides, carbides, and nitrides, and they are engineered for extreme performance. To put that into perspective, cubic boron nitride, which is one of these new ceramics, is actually the second hardest substance known to humanity, right behind diamond. No way, right?
So to really understand how these complex, incredibly stubborn materials are actually manufactured, we're going to follow the literal life cycle of a ceramic product from start to finish. We'll look at preparing the raw materials, shaping and forming them, the very real danger of drying, and finally, the firing process.
All right, step one, preparing the raw materials.
Our journey begins on the factory floor with some pretty violent beginnings. Before we can build anything up, we literally have to break the raw earth down. Because ceramics have zero ductility, we can't just melt them down easily or hammer them into shape like we do with metals. Instead, we have to take massive lumps of raw materials, stuff like kaolinite clay and fluxing feldspar, and basically use brute force to reduce them into a very fine, workable powder before we can even begin to think about shaping them.
And to do that, we bring in some incredibly heavy machinery. We've got the jaw crusher, which does exactly what it sounds like. This massive metal jaw toggles back and forth to just mercilessly crush large mineral lumps against a fixed plate. Then we have the hammer mill. This thing uses a series of heavy rotating hammers that violently impact the crushed minerals to break them down even further. It is loud, it's aggressive, and it's absolutely necessary to get the exact particle size we need. Once we've finally ground our raw material down into a super fine powder, we mix it with water to create something called slip. Now this is a crucial industry term, but don't be fooled, it's not just mud. We highly engineer this slip by mixing in very specific additives. Think of it kind of like baking a cake. We add a binder to hold all those stubborn particles together, a lubricant to reduce internal friction, and a plasticizer to make the whole mix much easier to mold. It's a very precisely calibrated recipe.
Moving right along to phase 2, shaping and forming.
Now that we have our workable slip, we can look at the completely ingenious ways engineers force these particulate mixtures into complex, useful shapes. Now, what's really interesting about this first method, which is called slip casting, is just how simple yet brilliant it is. We take our fluid slip and literally just pour it directly into a porous mold. That mold actually acts like a giant sponge, absorbing water right out of the outer layers of the slip. Once a thick enough layer has built up against the mold walls, we just invert it and pour out the rest of the liquid. When we open the mold, we're left with a hollow, shaped object that we call a green part. It's perfect for manufacturing large, complex things like plumbing ware. But what if we need a totally different shape? Well, if we use a clay mixture that has just 20 to 30% water, we can use plastic forming methods. We've got extrusion, where we force the clay through a die to create really long, uniform sections. Think of hollow bricks or drain pipes. Then there's an operation called jiggering. Here, we pop a slug of clay onto a rotating mold, and a specialized tool presses down to shape it. This is exactly how axisymmetric parts, like the ceramic dinner plate sitting in your kitchen right now, are manufactured at a massive scale.
So the crucial takeaway here is that how we shape a ceramic depends entirely on its water content. It's a direct, inverse relationship. Slip casting uses a ton of water and almost zero pressure. But as we use less water, the pressure required to form the shape absolutely skyrockets. For example, dry pressing uses below 5% moisture, but it requires massive mechanical pressure. This is totally ideal for churning out precise items like wall tiles or electrical insulators, because it creates a really dense part without creating any excess waste.
Okay, so we've shaped it. Now we enter section 3, and honestly, this is the danger zone, the drying phase.
We've got our shape, our green parts, but we are far from finished. 20%. That is how much a ceramic object can shrink from its original moist size purely through the loss of water during this drying phase. 20% is massive. If this shrinkage happens unevenly, the entire part will just warp or violently crack, completely ruining all of our hard work up to this point.
To understand why that happens, let's zoom in to the microscopic level. In a moist green part, there's all this interparticle water acting as a tiny spacer between the flat clay particles. During drying, that water migrates to the surface via capillary action and just evaporates into the air. As the water leaves, those solid clay particles are physically pulled closer and closer together. It shrinks the entire part, kind of like how a wool sweater shrinks if you accidentally put it in a hot wash. We have to control the humidity and temperature absolutely perfectly until those grains finally make direct physical contact.
And that brings us to phase 4, the final firing.
Once the part is safely dried out, it's still relatively fragile, so it's time for the climax of the whole manufacturing journey, the trial by fire. We subject this delicate green part to extreme heat to make it functionally indestructible. And this brilliantly illustrates exactly what's happening inside the furnace. This process is called sintering. We aren't melting the ceramic into a liquid pool. Instead, the intense heat causes the individual ceramic grains to actually bond together at the atomic level. See how those initial contact points physically grow into solid necks, eventually forming a dense network? That thermal forging is what drastically increases the material's strength.
Now zooming back out to the macro scale, this sintering happens in massive industrial furnaces called kilns. We've got tunnel kilns where carts loaded with products slowly pass through a hot tunnel on rails, hitting a blistering 1800 degrees Celsius in the middle. That's unbelievably hot. Then, for flat stuff like tiles, we use a highly efficient roller kiln. The products are placed directly onto a roller conveyor for incredibly fast firing that uses the absolute minimum amount of fuel.
Real quick, before we wrap up, we absolutely have to mention the final finishing touch, and that's glazing. While a fired ceramic is super strong, it can actually still be porous. To fix this, manufacturers will often coat the product with a glaze or an enamel. Yes, it does require a second firing step, but the heat melts that glaze into a beautiful, smooth, glassy, and completely impermeable coating. It improves both the strength and the final aesthetic of the product.
And that pretty much brings us to the end of our journey. We've seen how violent, crushing, precise chemical mixing, immense pressure, and blistering heat can quite literally transform the dirt beneath our feet into the engineered materials that power our entire modern world. It's amazing. Our mastery over manipulating these invisible crystal structures just continues to evolve every single day. From ancient pottery thousands of years ago to the advanced microelectronic substrates inside the very device you're using to watch this right now, what will we shape next? Thanks for joining me on this explainer, and keep exploring.